Okay, we're back and we're doing some mechanics. We're going to do some gravity. And in particular, we're going to do some strange shapes. We're going to do rings and sticks. And these are definitely different from planets or stars that we generally talk about, or point masses, where we just figure out the force of gravity using Newton's law. It's also different from another video that I have out there is for Gaussian shapes, that is spheres, cylinders, and flat objects, where the behavior of gravity differs depending on the geometry, the shapes of the objects. We're going to look at two shapes, or two types of objects, where Gauss's law does not work, and that would be a ring or a stick that actually does have ends. Now these are two shapes that Gauss's law does not work with. And instead, we basically have to take the one thing that we know for sure, which is how to find the gravitational field due to a point mass, which is big G mm over r squared. We need to break up the object into a bunch of point masses. And in reality, that's really what they are. Things are made out of atoms, which are point masses. And so we have to find the field made by each individual little piece of mass, and then add them all up. So that means we're going to have to figure out how to do integrals, and set these integrals up in order to do shapes like this. So here's a ring. Has a certain radius, has a total mass, and we're just looking for the gravitational field out on some point on the axis. Now, for a point mass, that's what this dm is up here. For a point mass, the gravitational field, or that little bit of a field, I guess we can call it dg, is out here on this axis, and it's pointing back towards that little chunk of mass. And this is going to be, just in terms of magnitude, I'm not going to worry about minus signs or anything. It's going to be big G, it's going to be the mass of the little chunk, and it's going to be over r squared. Okay? Where little r is that distance from the point on the ring to the point on the axis. Now this point that we're looking at is a fixed distance away, so we could just go ahead and say it's big G dm all over, let's see now, r squared is going to be the radius of the ring squared plus that distance out on the axis squared. Okay, so that's the field created by that one little point. Now, from the symmetry of this, because we're looking at this axis that goes right through the center of the ring, there's also a little piece of mass down at the bottom of the ring, same distance away, it's producing the same strength field, at the same angle. Okay, that's this angle in here. So those y components are going to cancel each other out. So really what we need to do is to figure out, okay, well, how much of this gravitational field is just in the x direction. So we still have the total field, but now we have to multiply it, only the x component survives, so we have to multiply it by the cosine of whatever that angle is. And we can use this big triangle to our advantage. And we can rewrite this as, it's looking like x over r, which is the square root of r squared plus x squared. So we can find this field due to a single little point of mass on the ring. To get the total gravitational field, or technically the acceleration of gravity along the x-axis, we just have to add up all those little fields. And that's what integrals do. Now in our denominator we've got r squared plus x squared to the 3/2 power. Now what's cool about a ring is that every point on the ring is the same distance and the same angle from the point on this axis that goes through the center. So really, x is a constant, r is a constant, big G is a constant. So this integral actually turns out to be not so bad. I can pull all these constants out. And what we're left with is just the integral of dm. That's just going to be the total mass. And so we end up with the x component of the gravitational field on that x-axis. Okay, so not too bad. It looks kind of weird because it's symbolic, but hopefully this gives you a sense as to what this process is. And really, that's the focus of this video, is really just the thought process, how to break things up into little masses. Perhaps you'll pick up how to set up these integrals. And in fact, for this next example, sort of stick, I'm not going to worry about solving the whole thing. I just want to get it to the setup. Okay. Now this one's a little tougher, a little more involved, and you'll see why in a second. So what we have is a similar situation. We've got a stick with ends, total mass and total length. It's producing a gravitational field at some point on the bisecting axis. It's the same thought process, the same strategy. We're going to break up the stick into a bunch of little pieces, little dm's, because we know what little bit of the gravitational field is due to that mass. Okay, so it's nearly identical. Oops. Don't need the square root. Okay, now in this case, it's going to look very similar. Y squared plus x squared is equal to r squared. We do have some symmetry because we're on the bisecting axis. We have another chunk of mass down here. It's the same distance away from the middle, which means it's on the same distance from the point on the axis. It's the same angle that we have here. The y components are going to cancel out, and so really what we're after are these x components. So we're going to have to integrate all of these little fields and then we have to multiply it by the cosine of the angle. Okay, so that's going to be x over r. Okay, so this is almost the same thing as what we just had for a ring. Okay. Now the difference is, what's our variable? Okay. What's going to change from little chunk of mass to little chunk of mass? And the answer is the y variable, that y distance. So we can't evaluate this integral as is. What we need to do is to be able to stick in a dy in order to evaluate this integral. Okay, now that's kind of weird because that means we have to write mass in terms of a distance. I'm going to use a little trick. It's kind of based off the idea of density. I'm going to look at the ratio, the total mass over the total length of that stick. And if everything's uniform, that ratio is just a number. Now it should be the same for the total stick as it is for any little piece of the stick, just like density, mass over volume. Okay, so by doing this, I really can write mass in terms of a distance, okay, using this ratio. And so what this integral turns out to look like once we make the substitution, we have g times x. Okay, now I'm going to substitute in dm, this ratio or constant times dy, all over this. There's also some limits on this integral. We want to add up all these little chunks from one end of the stick at the bottom, where y is equal to negative L over 2, to where y equals positive L over 2. Okay? And this is really where I wanted to get it. It actually does simplify down. We could pull out constants. All those values. But the rest we're kind of stuck with, and this is actually what the integral would look like. dy over this quantity, y squared plus x squared, to the 3/2 power. Okay, so this is where we'd want to take it. Okay, again, I'm not going to worry about what the answer is for time's sake. But whether it's the stick here, whether it's the ring up here, we're setting up integrals, we're thinking of things as little point masses to find out the individual fields. And what integrals do is it's a summation. It's going to add up all the little pieces of gravitational field until you get the exact total. Okay, so think about these integrals. It'd be pretty rare that we'd ever see anything like this on the AP exam, but at least you kind of know what's going on with this. You can acknowledge that the calculus does become a powerful tool for something like this. We'll come back to this in electricity and magnetism next year for electric fields and magnetic fields. Very similar types of ideas and integrals. But the point is, yeah, that there's a process here in place that we can make use of. I hope this helps, and until next time, we'll see you later.